Welcome back to the series on robot path planning. Today we shall be discussing artificial potential field method. Slides are based on the book by Hui Chose, which is a famous book on robot motion planning, theory and implementation. Simple idea of the method is that the configuration space is assumed to be an artificial potential field that draws the robot to the goal and repels it from obstacles in the environment. Let us think that the robot is at a higher potential energy level and goal is at a lower level. Naturally, the robot will move from higher level to lower level and definitely it will be avoiding the obstacles. Imagine that the robot is having positive charge, obstacle is also having positive charge, and think of the goal having negative charge. So in that case, there will be a repulsive force acting against each other between robot and the obstacles. To model the artificial potential field, let us first define the potential function U from Rm to R, where Rm is considered to be the configuration space and R is the field of real numbers, that is the scalar field. Energy is minimized by following the negative gradient of the potential energy function because the gradient points to the maximum rate of change, if you remember. Now at each point of the vector field, which is the our configuration space, what the robot will look for? It will look for the vector, that is the gradient vector, and will go in the negative direction. I hope you remember that gradient is defined as a vector having components as the partial derivative at any point. Note that we have to model two different types of potential. One is attractive potential, the other is repulsive potential, here denoted by U attract and U repulse. So the combined field or combined potential will be a combination of attractive and repulsive potential. Let us first model the attractive potential function. Distance between the current configuration and the goal can be considered as a good candidate for attractive potential. I multiply it by a constant. This constant is only to scale up or scale down the value of UQ. Suppose the robot is at this location, say Q, and the goal is at this location Q goal. For short, I am writing QG. This distance multiplied by a constant xi is the value of the potential function. In order to find out the gradient of u, let us consider for the moment that q is only two-dimensional, consists of x and y. So q goal will also be two-dimensional, say x0, y0. Euclidean distance is given by x minus x0 whole square plus y minus y0 whole square, take the square root. Now, if I have to find out the gradient, you know that you have to find out the first partial derivative with respect to x and also the partial derivative with respect to y. Let me calculate del u by del x. Now, del u by del x will be nothing but 1 upon 2. Let me take this quantity, inner quantity, call this as, say, a. Let me call this as a. So 1 by 2a to the power minus half multiplied by derivative of a with respect to x. So that will be nothing but 2x minus x0. So you can see that del u by del x is simply del u by del x here, let me write down, is nothing but x minus x0, distance between q and q0. Similarly, del u by del y is also equal to y minus y0 divided by dq q0. This can all q goal that can also be found out, and hence gradient of u can be expressed as psi times q minus q goal divided by distance q and q goal. Well, this is a simple method, easy to compute, for defining attractive potential. But there's one issue with this method. Suppose Q is here and Q goal is here. Now, when Q approaches Q goal, certainly the numerator goes to 0 of the gradient of delta, gradient of UQ. At the same time, the denominator, the distance between Q and Q goal, also goes to 0. As a result, gradient of UQ tends to an indeterminate form, approaches an indeterminate form. And therefore, finding out the direction at a position which is very close to 0, close to goal, is not feasible. And this gives the singularity case. So that is the problem with this definition of conical potential. Another model could be a quadratic potential function, where in place of distance function, we take its square. So 1 by 2 xi, which is a scaling constant, d square q goal, where d is the distance between q and q goal as before. Now let us see what is its gradient. Now because here d square is present, so let us consider the previous case. So here the distance is, for short I am writing distance as x minus x0 square plus y minus y0 square. Because I have to take the d square term, so distance square will be this. You can see that its gradient will be 2 times x minus x0, 2 times y minus y0. Right? So when we take its gradient, it turns out to be this. When we multiply it with 1 upon 2 xi, then this 2 cancels out with that, and we are only left with xi q minus q goal. So you can see that the gradient function here takes a very simple form. Quadratic potential functions have one issue, that they grow very fast when the robot is far from the goal location because of the quadratic term present there. As a result, robot's velocity will also be high. And in such cases, one would not like to have a high velocity at a farther location for two reasons. One could be an energy optimization criterion. The other could be if the velocity is very high, it may be difficult to control the robot and it may hit an obstacle in surrounding area. Conical potential function, on the other hand, lead to singularity in gradient. Let us see how a combination of these two can be a useful solution. So this expression of U attractive at Q, that is U attract Q, attractive potential, is a combination of these two functions. So when the object is closer to the goal, or the robot is closer to the goal, I will be using a quadratic function as shown here. And when the robot is farther from the goal, then I will be using a conical function as a solution. Here you can see this circle surrounding the Q goal, that is goal location. On this circle, the distance function, the distance value is equal to d star goal, which is a threshold that we set. So if the distance is below a threshold, I will be using a quadratic function as shown here in green box. And if the distance of the current location from the goal is higher than the threshold, then I will be using a conical function as shown here in red box. You must have noticed two important terms here. One is this multiplying value d star goal, and another is subtracted 1 upon 2 psi d star square. This is done to maintain continuity when we are using two definitions. One is for higher values of d and the other is for lower values of d. So when the robot moves from higher value of d to a lower value of d that is closer to the goal, then there should not be any discontinuities between the potential function. You can verify that at the value when dqqq goal becomes d star goal, the two values match. In addition, if I look at the gradient function, which you can compute easily, the gradient function also is continuous at the boundary, that means at the circular boundary that is shown here. Here is an example of an attractive potential function which is constructed using a combination of both quadratic function and also the conical function. Here is a numerical example also. Suppose the goal is at location 3, 4 and the current configuration of the robot is specified by xy, which will keep moving. For the sake of simplicity, let us take scaling parameters I to be 1 and also the threshold that we have set is 1. In that case, the attractive potential will have this form 1 upon 2 square of the distance when the distance function is less than or equal to 1, and it will be equal to distance minus half when the distance is bigger than 1. And the gradient in that case will be simply the difference between the current position xy and 3, 4, that is a vector pointing xy minus 3, 4 when the distance is less than or equal to 1, and uh, it will be the same vector divided by the distance function when the distance is bigger than 1. So it is easy to see that continuity conditions are met because we have added these constants and suitably modified the functions in both the domains when the distance is less than a threshold and distance is bigger than a threshold. Let us now move on to the definition of repulsive potential. Suppose the robot is at a configuration Q and its distance from an obstacle is capital DQ. Suppose capital DQ is bigger than a threshold Q star, then there is no point of taking a positive value or any non-negative value of repulsive potential. Therefore, I will choose it to be 0. That means robot is at a safer location. But if robot comes closer to the obstacle, that means if the distance of the robot dq is less than q star, then I should be using another definition which is shown here. Now when dq becomes q star, you can see that the value becomes 0 of the function, which is this. Therefore, continuity is maintained from within the two regions. You can also see the gradient function. The gradient of u repulsive is also defined as a combination of these two values. And you can see here too that the gradient function is also continuous. Let us take a numerical example where Q is again the current robot configuration, and suppose 1, 1 is a point on an obstacle which is closest to the robot's current configuration. Then dq will be the distance between 1, 1 and xy. Let us choose a scaling parameter to be 1 and also the distance threshold that we are setting to be 1 for defining the hybrid definition. Then U repulsive Q will be half multiplied by 1 upon distance minus 1 whole square if the distance between the robot and the obstacle boundary point is less than or equal to 1, and it will be 0 beyond this boundary or beyond this threshold. You can also compute the gradient and see that continuity is maintained when we move from a region where the distance is less than 1 to a region which is greater than 1. This is an example of a repulsive potential showing two obstacles. So when there are two obstacles in the scene, the repulsive potential will look somewhat of this type. Now, total potential function is a combination of attractive and repulsive potential, and the force acting on this will be based on the gradient of this total potential function. So this is an example showing a combination of attractive and repulsive potential function at a configuration Q. With single obstacle, we know that there will be only one repulsive force. But if there are multiple obstacles, then how do we compute the repulsive potential? For this, let us first consider how the distance between the current configuration and the obstacle is computed. It is basically the closest point that is sensed on the obstacle. That is considered to be the closest point, and the distance between the current configuration and that closest point is considered to be dq, or the distance, in the formula for repulsive potential. If there are n obstacles in the sensing range of the robot, then the repulsive potential is computed as the sum of all repulsive forces, as you can see here. Once the potential energy function is defined, let us find out its minimum by gradient descent method, which is a simple method to obtain a minimum. So suppose Ct is the path the robot is following with respect to time, then minus of the gradient of u at the configuration Q, which is at a position Ct on the path, will be obtained to find out the minimum. Now we know that a critical point is a point Q such that gradient of uq is 0. So function shows stationary behavior at a critical point, you all know, but that could be a maximum, minimum, or a saddle point, as is shown here. In all these cases, you have a saddle point, a minimum, or a maximum, but the function is showing stationary behavior at that point. Hessian matrix helps us understand the behavior further of the critical point. Hessian, in this case, when you have a m-dimensional configuration space, will be an m cross m matrix of second derivative. For a two-dimensional configuration space, it is given like this. It is del 2u by del x square, del 2u by del x del y, and so on and so forth, as you can see here. And if the Hessian is non-singular, then the unique critical point can be a minimum if it is H is positive definite. That means Q transpose HQ, which is a real number, is greater than 0. If this is less than 0, then you will get a maximum, or when H is negative definite, and it is a saddle point if H is indefinite, or none of the above conditions are satisfied. Let us now move to gradient descent method. So we start with the Q start, that is the current location, initial location of the robot, at time step I is equal to 0. We also use a threshold to run a loop where if the gradient is below this threshold in magnitude, then we will stop. We also have a gradient descent rate alpha. So while this magnitude of the gradient at any time step I is greater than threshold, we will choose the next position qi plus 1 as the current position or current configuration minus alpha gradient uqi. That is, we are moving in the opposite direction, but the rate is alpha, descent rate is alpha. Then we go to the next step, I is equal to I plus 1, and this keeps on repeating until what happens, that the gradient diminishes or is less than the threshold. You may also choose alpha to be variable depending upon the current location and the scenario. If there are no obstacles, we are away from the robot, the final goal location, then we can move fast, so this rate of descent can be large. If you are having obstacles around, then you can have a smaller rate alpha. Often continuous distance computation is not practical, and hence discretization of the distance function is important. Brush-fire algorithm is one of the first algorithms that computes distances using a discrete function. Brush-fire is one of the classical algorithms that is used to compute distances which are used in repulsive potential. It transforms the distance function to a discrete function. Remember that this algorithm only computes distances, which is then used in a path planner. So it is not a path planner. For this, we assume that the entire environment map is represented on a grid domain. That is, it is divided into grids. Connectivity between two grid cells is defined using either a 4-connectedness or 8-connectedness. So for a 4-connected cell, you can see on the left we have 4 adjacent cells, up, down, right and left. And in 8-connected cell, we have all surrounding cells which are neighbors of this cell. Let us now see how brush-fire algorithm works. Here is a gridded environment in which there is only one obstacle. So we first label all cells overlapping with an obstacle as dt is equal to 1, and rest of the cells are labeled as 0. We initialize a list L to be empty, and while C is on the boundary of the obstacle, I will push C to L. For example, here we have all these cells which are on the boundary of the obstacle, and therefore they will be all pushed to L. While L is non-empty, I will pop up the top element from L, say T, and then I will relabel it. To relabel it, what do I do? If I consider, for example, this is my T, the current T, which is right now labeled as 0. Its neighbors are, this is one neighbor, this is second neighbor, the third neighbor, and the fourth neighbor. Out of these neighbors, only one neighbor cell I will be choosing whose value or the label is non-zero. Rest of the neighbor cells have 0 value, so they will not be considered. Remember that here dt has to be non-zero for a neighbor. So there is only one neighbor cell. I will be setting the current cell's dt value to be 1 plus the minimum of the neighbor cells whose labels are non-zero. So in this case it is 1. So I will be setting this 1 plus 1, that is 2. So this cell, which is shown here by highlighted by red color, is having label 2. Then what I will do is pushing all the neighbor cells of this cell to the list L, which are having 0 label. So 0 label are these cells, like this one is 0 label, this one is 0 label, and the third. So all these three will be going to L. In this way, all the cells will be labeled, and at any cell, the label shows that how far it is from the obstacle or proportional distance from the obstacle. Potential field method faces some issues with concave obstacles or certain kind of obstacles because local minima occur. For example, in this case, here is the goal and here is the starting point for the robot. As per the potential function calculation, it will be moving along this curve, and at this point it will be stuck because it will think that this is a local, it will think that this is a minimum, whereas this is not a global minimum, it is a local minimum. Similar situation happens here when you have goal here and starting point is here. Because of these two obstacles present, it will be stuck in a local minimum issue. If we apply brush-fire algorithm to compute distances from the obstacles, to apply to gradient descent method for repulsive potential calculation, then we may face problem, as we saw, if there are obstacles which are concave or different positions of obstacles. So we apply brush-fire algorithm using the same concept as brush-fire algorithm. We start applying it from the goal. This is known as wavefront algorithm. So let us see how we apply it on the starting from the goal. So we have an environment in which, suppose the goal is somewhere here. This is my goal. I will be labeling this goal cell to be 2. Suppose it has 8 connectivity. This environment that I am having is considering 8 connectivity. Then all its neighboring cells, in fact all the cells in the environment, will be labeled as 0 except those which contain the obstacle. So here is an obstacle. Because these cells are containing obstacle, so they will all be labeled as 1. So 1, 1, here this is 1, 1, 1, 1, 1 and 1. And now you can see that we have here, these are all labeled as 0. Then what I will do, when L is non-empty, again these cells which are labeled as 0, which will be all labeled here, will be put in L, and I will pop the top element of L, and that will be called as T. Let me consider that top element as T. So suppose I consider this cell. Now this cell is having 2 as its neighbor. So I say that set dt to be 1 plus minimum of all its neighbor cells labels, such that neighbor cells are having labels greater than 1. So I will be considering all its neighbors. Suppose there are 8 connectivity, then this is a neighbor, this is a neighbor, this is also a neighbor, this is also a neighbor, and G, which is goal, is a neighbor for this cell which is marked here. Now it has three different types of neighboring cells. Those which are labeled as 0 will not be considered. Those which are labeled as 1 will also not be considered, because here we take only those cells which are having label greater than 1, right? So only cell which is the goal cell will be considered for computing the distance dt, in this case for the cell which is shown here. So this cell will have label 1 plus minimum dt, which is 2. So it will have label 3. Okay. Then I will push all the t prime belonging to nt, that is, which are having label 0 and which are the neighbor cells of the current cell. So what will be these? These will be the one which are like this cell is a neighbor, this cell is a neighbor, and this cell is a neighbor. All these three cells will be pushed to the list L, which are having label 0. But this cell which is having label 1 will not be pushed to L because it is having obstacle in its is overlapping with the obstacle. So this defines a distance of every cell from the goal. In fact, it is proportional to distance which is from the goal. Gradient descent then can be applied to move to the neighboring cell with lowest distance value from the current position to reach to the goal. Let us consider an example of a wavefront planner. In this scenario, we have a start location, which is this, and a goal location, which is this. And because of the obstacles present, these cells are marked as 1. The rest of the cells will be marked as 0. You can choose a 4-point connectivity or an 8-point connectivity. In this example, we've chosen 8-point connectivity. You can see here that these cells are all labeled as 3 because their neighbor cell is labeled as 2. So I'll be choosing minimum of those labels which are non-zero labels, which are greater than 1 in fact. We keep on repeating labeling with modified cells until no zeros are adjacent to cells with values greater than or equal to 2. Remember that zeros will remain only when the regions are unreachable. For example, in this situation, if suppose you have uh, the obstacle which is somewhere here and also somewhere here, then these points are totally unreachable, which are here. So they will never be relabeled by any other non-zero number. We keep on repeating this process of labeling. As you can see, it is labeling is moving ahead like a wave. Finally, all the cells will be filled with non-zero labels except those which are unreachable. Here in this case, there are no unreachable cells, so all the cells are labeled with a non-zero value. Now to find the shortest path, we apply potential field method, moving from higher potential to lower potential value. And so from a given cell, here we have a start location as we saw before, labeled at 18, and the goal location is labeled at 2. So we can see that we will move towards a cell which is at a lower potential. All its neighbor cells are at 17 label. So I will be going this way, then this way, 14, 14, and then in this way I will be moving ahead with a lower value at each time step. And finally I can reach here. So there can be many shortest path and the number generated by wavefront planner are roughly proportional to the distances from the goal. Here is another example of a shortest path. Most of the slides of this lecture are based on the slides taken from here, which is the lecture slides of Hui Chose from Carnegie Mellon University. And the figures are also taken from the book, as I told before. Implementation of many path planning algorithms you can find in this wonderful website, which is a GitHub page on Python robotics, including artificial potential field method that you can find there. That's all for this session. We'll be discussing more on path planning in our next session, particularly shortest path algorithms. Thank you.